Hello, everybody. It looks like we have a good showing tonight, so that's good news. Everybody's interested in doing these acids and bases, I'm sure. Yeah. All right. So there might be a few more people joining us. We'll see. So does everybody got a chance to grab the problem solving session worksheet for tonight, I assume? Yes. All right, I'm seeing some yeses in the chat. Of course, we can. Abdullah wrote in the chat that he wants to go over problem 3 on the homework. You want to do that before we get started? We can do that. All right, what is problem 3?
I can share my screen if you want.
I have it up. Does everybody have problem 3 up from the homework? Okay. Well, let's go over that quick and then we can do what it is that we were set out to do. Okay. So what I'll do is I'll share a whiteboard. All right, I'll share a whiteboard. And this question asks about carbonic acid and bicarbonate in human blood. Okay, so we're going to say that ratio, or that carbonic acid bicarbonate is 25 millimolar total. So that means the total of carbonic acid and carbonate or bicarbonate added up. So the total is 25 millimolar at pH 7. Okay, so it asks for the ratio of carbonic acid to bicarbonate in human blood. Okay, so here you're going to invoke the Henderson-Hasselbalch equation. All right, so the pH here is 7.4. The pKa of carbonic anhydride, or sorry, carbonic acid is 6.37. And I see that it doesn't say it in the problem, but that could be something you look up, what the pKa of carbonic acid is. All right, and so we want to solve for the log of base, which is the bicarbonate, per acid. And that'll give you the ratio, okay? All right. We know that base plus acid, so we get the ratio, we know that the base plus acid is equal to 0.025. Okay, so once you know the ratio and you know what the total concentration is, you can solve for the concentrations. And did you use that link?
Was it in the homework?
Mm-hmm. Was it not? It's in mine that I brought up.
I don't see anything.
Oh. Did you grab that? Okay, good. All right, so then when you solve for, so if you know what the ratio, so this is kind of like an X and Y problem. You know what the X divided by Y is equal to, and you know what X plus Y is equal to. So you have two equations, two unknowns, you can solve for it, all right? And so that's a quick and easy way to do it. So when you do that, you get bicarbonate, so the base, oops. So the base is equal to 0.0229, and your acid, which is your carbonic acid, is equal to 0.00213. All right, Abdullah, were you able to do that with that link? Okay, awesome. All right, so it works. All right, so everybody else, you can try this. This is essentially just two equations, two unknowns. Okay, so now the next step is how much carbonic acid and bicarbonic acid does a liter of blood contain? Okay, so we know that we just solved for molarity, which is moles per liter. So we have 0.0229 moles of bicarb, and we have 0.00213 moles of, sorry, my 2 looks terrible, 213 moles of carbonic acid. All right, awesome. All right, so now if you know the moles and you need to get, it's asking for moles, so this would be your answer, right? I thought we were gonna have to solve for grams there. No such luck. All right, so that's B, okay? Now for C, it asks, determine the pH if you add 10 mils of 1 molar HCl to 1 liter of blood. Okay, so first off, I'm going to ask Sana, if I add HCl to this mixture of bicarbonate and carbonic acid, which of these is going to react with the HCl? The bicarbonate or the carbonic acid? Yeah, you're right. You're going to react with the base. So the H, CO3 minus, and we're going to form the acid, which is H2CO3. Okay, so it asks here, so that's our reaction, and our moles of HCl is 0.01 moles. Okay, so we have 0.01 moles that we're going to add to this solution. We have 0.0229 and 0.00213, okay? So we know that this one is going to decrease, right? It's going to be consumed by the HCl, and we know that the amount of carbonic acid is going to increase, right? So we're going to subtract 0.01 and we're going to add 0.01 over here. And then we just do our math to figure out how many moles we have in the end. So we have 0.0129, and we have 0.01213, and this is in moles, okay? Now, if we want to find the concentrations of these, we have to then divide by the volume, okay? But if we're going to put this right into Henderson-Hasselbalch, we don't necessarily have to solve for the volume. You can use moles in this case because the volumes will cancel each other out. It's just a ratio. Okay, if I clear the screen, everybody? Okay. So I'm going to clear my screen here, and then I'm just going to solve for the Henderson-Hasselbalch equation. So we want to know what the pH is after we have added that much HCl. So we have our pKa plus the log of our base over acid. So our base was 0.0129, and our acid is 0.01213. Okay, so who can calculate that for me? What is my pH that I get in the end? Okay, 6.4, good. All right, so we solve for the pH after adding some amount of HCl to the solution. Okay, so notice that the pKa is 6.37. Our new pH is 6.4. So we are resisting changes to pH. All right, that's the point of a buffer. All right, so the question here, the next question is, okay, so what if I had 10 mils of 1 molar HCl that I added to 1 liter? Okay, and so we have 0.01 moles of HCl from the 10 mils of 1 molar, and we're going to divide by our volume, which is a 1.01, because we added 10 mils to 1 liter, and we get 0.0099 molar. All right, awesome. Now, how do I find the pH here? What do we know about HCl? Strong acid, all right? So I'll just take the negative log of 0.0099, and what do we get? Yeah, 2, awesome. All right, so let's compare. pH is 6.4, real close to our pKa. pH of 2, not so good. All right, so pure water is going to be about 7, right? If it's absolutely pure water. And just adding a little bit of that HCl brought us down all the way down to 2. So the question here is carbonic acid in blood, is it a good buffer? Yeah, sure is. It's doing its job. It's resisting changes to pH. All right, I think that was all of number 3, right, everybody? That sound good? I think Abdullah was the one that asked the question. Are you satisfied? Okay, awesome. All right, so should we get back to the problem at hand, everybody? Yay, let's do it. All right, so I was thinking about how to do this. And I know that everybody hates breakout rooms. And so I try to be very, I don't know what to say. What am I trying to say? Definitive, direct with how I do breakout rooms. And sometimes things don't require breakout rooms and it's better to work together. Okay. This is neither of those things. So what we're going to do is we're going to shake things up a little bit. We are going to split up into 6 groups. So if you have, I don't know if you have this electronically or if you have a piece of paper, however you have it, what I want you to do is write this down. Okay. So room 1 is going to work on number 1. Room 2 is going to work on number 2. Room 3 is going to work on number 3. Room 4 is going to work on number 4 and 5. Room 5 is going to work on 4 and 6. And room 6 is going to work on 7 and 8. Did y'all get that? Okay, so I'm going to put you into 6 groups, all right? And by your group number, you're going to know what you're working on, okay? And then in the end, we're going to come back together and each group is going to show us that problem that they were working on. So you can nominate somebody that will be your leader to either share your screen or somehow talk us through it and teach us the problem, okay? So every group is in charge of their own problem, okay? Sound good? All right, let's do this. All right, I'm gonna put you into 6 groups.
Really bad.
There's also a cup in my bathroom.
I know.
Can you close the door, please?
Well, tomorrow class, because there's a new update. There's a new skull font. It has white eyes, but a normal skull font has different color eyes. But you know it's the new skull font because there's a crack in the head, and every single boss is there.
Okay.
You want Bella in here? Bella's in here.
Okay. You know what? Then don't close the door. Just kind of sort of close it.
You're muted, Dr. Stone.
It keeps doing that. Thank you, Nick. So I believe that if not all of you, most of you were able to get through your problem that you were assigned. So hopefully you remember which groups you were in, because I'm going to call you out by numbers. And I want you to, hopefully you already nominated someone that's going to be your leader, because someone's going to take us through how you solved your problem. Okay, so we're going to start at the top. Let's start with group 1. What is the
Yeah.
pH?
I have no idea. Like, I understand how to get the pKa value, but beyond that, because we have no like concentrations to work with, like we have 0.1, right?
Mm-hmm.
And we could do an ice table, but like I don't know like what to even subtract, what to even do with that to find like the concentrations between like the acid and the base. I'm kind of lost.
Okay, well, it helps to do an ice table. Let me show you. All right, so you could do this with an ice table. And so here, let's just write out the reaction. So you have this salt in water, and it forms NH3 and H3O plus. All right, so your ice table. 0.1, 0, 0, minus x and x, 0.1 minus x and x. All right, so now, did you solve for the Ka of for ammonium?
The K or like the pK in the Hasselbalch equation. Honestly, I didn't realize that like it was in water solution, so I never really understood like this that we were going to this part. So
Okay, so tell me what the Ka is.
the Ka would be x squared. Well, K would be NH3 times H3O plus over over the NH4 or the other thing.
So if you solve for the Ka knowing the Kb, you should get,
Oh, negative 9.26. Right?
oh, right, that's the pKa. So I was just looking for the Ka first off, okay? And I'll tell you why in just a second. So here's our Ka. So 5.6 times 10 to the minus 10. So if we want to solve, I fear that I may have led you astray when I was first talking to you, because this is not a buffer solution. This is a straight up salt solution. And so the only concentration we need here is the concentration of ammonium, okay? Because if we set up the Ka expression, it's x squared over 0.1 minus x. So just like a typical ice table. Is that helpful, Nick?
Yeah, makes a
Okay.
lot more sense.
Okay, so let's assume x is small. Now I want you to take 0.1 times 5.6 times 10 to the minus 10 and take the square root of that to solve for x.
That is 7.5 times 10 to the negative 6.
Okay, so 7.5 times 10 to the minus 6. Take the minus log of that, please. Because you just solved for H3O plus concentration. Now let's solve for pH.
5.12.
Perfect. All right, sound good?
Yep.
Yeah, you're gonna have to be able to do a lot of these problems. So hopefully you get some practice. on taking just a solution, whether it's a weak acid or a weak base, and finding the pH of that solution. All right, so I'm going to stop sharing here. Now I want group 2 to jump in. What'd you get for group 2? The rearranging or deriving the Henderson-Hasselbalch.
Yeah, so for the Hasselbalch equation for a weak base, it's POH is equal to PKP plus the log of acid over base. And it's similar to the equation for the weak acid in terms of the setup, but it's different because the weak acid looks at pH, and that's equal to pKa plus log with base over the acid, instead of acid over the base in the weak base equation.
All right, thank you, Akbar. Can I jump in for just a little bit here? So this, in your notes, in your slides, this was solved for a weak acid solution. The difference here is that you have base plus water forms the protonated base. All right, so just like he was saying, so now you're solving for the OH minus or the POH, okay? All right, so if we set up the expression for Kb, it's equal to the concentration of your conjugate acid times OH minus over the concentration of B. Okay, so that's just the simple Kb expression. So if you solve for OH minus, just like before when we solved for the H3O plus concentration, so if you solve for OH minus, what you get is Kb times the ratio of B over BH. All right, with me so far, everybody? Okay, now we're going to take the negative log of each side. All right, so negative log over here, negative log over here. And what we end up with, so negative log of OH minus concentration is POH. The negative log of Kb is PKb. All right. All right, and then to switch that sign from negative log of B over BH, we flip that ratio to be plus log of BH over B. Sorry, writing with a mouse is not easy for me. All right, so POH equals PKB plus the log of BH over B. All right, sound good, everybody? Okay, good, yeah. So Akbar, what you did was absolutely correct. I was just gonna go a little bit further for everybody, okay? All right, let's move on to group 3. They were picking out buffers for us, everybody. Tell us about that.
I can share my screen.
Awesome, thank you.
So just would be like the buffer has to be the lowest value for the buffer has to be for that. So and then the highest has to be this. So then it's pKa plus or minus 1. So then, but then like we have to pick a buffer that's closest to the pKa has to be closest to the pH that we want. So that would mean that sulfuric acid would be the closest buffer.
Mm-hmm.
Then,
But really, both of those will work, right?
Yeah.
Yes.
Yeah. And then for the second one, it would be this buffer because the rest of them are either too high or too low.
Mm-hmm.
Yeah.
Perfect. Okay, thank you, group 3. All right, so they picked out some buffers for us. Now we're going to work on 4 and 5. That was group 4. So group 4, you're going to tell us about number 4, but when we go to group 5, you can skip that part because we've already heard it. Okay, so let's have group 4 do number 4 and 5.
Okay, so for the first part of the question, it says to look up the pKa values of citric acid. And when you look it up, it gives you 3, but in this equation, we're going to use a pKa value of 3.1, and that's just because of the chemical formula of the given citric acid. And then we're going to use the Henderson Hasselbalch equation to find the pH. So we're going to say pH is equal to that pKa value of 3.1 plus the log of the concentration of the base over the acid. And we know that our base is our sodium citrate, which has a concentration of 0.18. So that's going to go on top. And on the bottom is going to be 0.14, which is the given concentration of citric acid. So when you plug in all those numbers, you should get a pH 3.21.
Good. All right, let's look at case 2.
For question 5.
For number 4, so the second part.
Oh, I didn't realize there was a second part.
Oh,
Oh, I'm sorry.
no problem. That's okay. Let's just move on to 5 then.
Okay. So kind of like the problem that we had done from the homework question 3, to this buffer, we're going to be adding 10 milliliters of a 1.09 molar HCl solution. And so we're going to write out our equation as HCl plus sodium citrate. And we chose sodium citrate because we know that's our base and that the hydrochloric is our HCl is an acid. And that's going to yield our citric acid. And then looking at it, we know that we can figure out the moles of HCl if we first convert the given 10 milliliters to liters. So we have 0.01 liters, and we're going to multiply that by the given 1.09, and that will give us 0.0109 moles of HCl. And then following that same logic for the sodium citrate, instead of using the 10 milliliters, we're going to use the 250 milliliters because that's a part of our buffer. So we're going to multiply from question 4, take that concentration of 0.18, and we're going to multiply that by 0.25, and that's going to give us 0.045 moles. And then that same process, we're going to take 0.14, which was given in question 4, and multiply that by the 0.25 liters, and that's going to give us 0.035. And then we know that HCl is in the lowest, has the lowest amount of moles, so it's going to, I guess, be the sodium citrate is going to use up all the HCl. So we're going to subtract the amount of moles from of HCl from our sodium citrate, and then add it to our
Oh, yeah, go ahead. I'm sorry. So
to our
so
citric
you're
acid.
subtracting from the sodium citrate and adding to the citric acid, right?
Correct.
Okay, good.
And
Thank you.
when we do that, we are going to be left with 0.0341 moles of sodium citrate and 0.0459 moles of citric acid. And then to use our Henderson Hasselbalch equation, we have to convert those back to into concentrations. And we're going to do, starting with sodium citrate, if we multiply the 0.03441 moles that we just calculated, or if we divide it by 0.25 liters, we're going to be given a concentration of 0.138.
So Connor, can I just stop you for there?
Yeah.
So if you want to get back to concentration, you have to add 250 milliliters plus the 10 milliliters. But to be honest, that's taken an extra step. And the reason I say that is because in the Henderson-Hasselbalch equation, it's just a ratio. So just go ahead and put the moles in. Save yourself some time.
Oh, I didn't even realize. Okay.
Because those are the same volumes, they'll cancel each other out.
Yeah, that makes sense.
So if you just go ahead and put those moles in to that ratio, then that's really all you need to do. But I know you took the extra step, so tell us all about it.
We just converted those moles that we had calculated back into concentrations by dividing by the liters, which it's the same answer regardless. So in this case, we got the concentrations of 0.138, which still wasn't the total volume, but it was just the volume of the buffer. So when we go back and we use the Henderson-Hasselbalch equation, we're going to take that same pKa value that we were given earlier, the 3.1, and we're going to add that to the log of, and in this case, just to save time, we can add it to the log of 0.0341 divided by 0.0459, which is just the moles of the base over the moles of the acid, and our pH is going to equal 2.98.
Awesome. Thank you, Connor, for that.
Yep.
All right, so group 5, take it away. You don't need to rehash number 4, just talk about number 6. I think that was Anna and Abby, right?
We had 7 and 8.
Yeah, it was our group. We actually spent all of our time doing number 4 and didn't get to number 6.
Oh, okay. So why don't we have Abby and Anna tell us about 7 and 8, because it's exactly the same procedure. So, sound good?
Yeah.
Okay, awesome. Why don't you tell us about number 7 and 8? So 7, we're using the Henderson-Hasselbalch equation, and 8, we're doing that same thing where we're going to talk about the effective capacity.
Okay, so for number 7, we used the Henderson equation, and what we did was found the pKa value, which was 10.3, and then added log, and then did base over acid, which is like 0.72 over 0.53, and got the pH of 10.4. And for number 8, we were still working on number 8. I'm not sure how to really explain it because I'm kind of having trouble learning it.
Okay, so it looks like you guys both ran into the same issue with capacity. Okay, so I'm going to take it from there. So let me talk about number 6. Okay. All right, so number 6 is asking for the capacity when we add HCl. Okay, so we know how much acid and base we have. And so what we can say then is that if we're adding HCl, how much can we add? And so the acidic part's on the bottom, and so the options here are either, is it going to be 0.1 or is it going to be 10? Because the acidic is on the bottom, the ratio here is going to be 0.1. Okay. And we know the amount that we have of the conjugate base and the acid. All right, so I want you guys to think about, so if I'm adding a strong acid to this reaction, is it going to react with the acid or the conjugate base?
The conjugate base.
Yeah. So what we'll do then, because base is on top, is we'll subtract that amount of HCl that we're going to add, because we're trying to figure out how much that is. and we'll add to the bottom, because that's what's going to be formed, that amount of HCl that we're going to add. Okay, then we can solve for X. And when you solve for X, you should get 0.0441, and that's moles of HCl. That's how much we're going to add if we're going to get to the edge of our buffering capacity. Remember, tenfold each way is the edge of our buffering capacity. All right, so we know the concentration, we know the moles, we can solve for the liters. So we'll take 0.0441 and divide by 1.09 molar. So this is moles, that's molar. So we're solving for liters, and that gives us 0.04 liters or 40 milliliters. All right, Charlene, is that helpful?
Yeah, thank you.
Okay. All right, so then let's go on to number 8. Let's go on to number 8. So this is opposite, and so what I have is not what you have. So you'll have to bear with me and have to shout out some numbers for me. But here we have a solution of sodium hydroxide that's going to react with this carbonate and bicarbonate. Okay, so because it's going to form the conjugate base, that means our ratio here is going to be 10. All right, that's the edge of our buffering capacity. All right, so 10 is 0.72 over 0.53. Okay, so which one is going to increase? Which one is going to decrease, everybody? Sodium hydroxide reacts with what? The acid or the conjugate base?
The acid.
Yes, the acid. So the acid is going to decrease and the conjugate base is going to increase. So it's exactly opposite of what we did before. Okay, so conjugate base is going to increase and the acid's going to decrease. Okay, so you can solve for X. So Anna and Abby, did you solve for X there?
Yeah, I got 0.42.
Okay. Right. And then you can solve for volume by taking your moles and divided by the concentration. And Abby, I don't have it in front of me. What's the concentration of sodium hydroxide?
You mean the KOH?
Or KOH, sorry, potassium hydroxide.
Oh, it's 0.09.
Okay. All right, and so what do you get for your volume here?
Four 4.7.
Hmm?
4.7. Unless I did it wrong.
Yeah, I got that too.
Oh, wow, that's a lot. 4.7 liters? I guess that makes sense given 0.42 moles. Okay, yeah, that's a lot because that's pretty weak base. All right, so I'm gonna stop sharing. All right, so we did get through this. It was tough, but you guys muddled through and you did great. Do you feel like you learned something today? All right, good. Thank you, everybody. I'm so glad. This is the point of this whole thing that we're doing, is that you guys learn something and that all of the things that we've been talking at you all week become a little bit more clear. Okay. So I guess with that, we're all done. So I'm going to ask, do we have any other questions that we need to address? All right. Well, you guys have a wonderful weekend. So glad to see you out here on this beautiful Thursday night. All right. So until just a second with that, okay? Everybody have a good weekend and oh, thank you. All right. Bye-bye, everybody. So I'm sorry, Amtul, what were you saying? My friend Abdullah wanted to make sure he is. I took a screenshot.